Yeah, last month I gave a real seminar, and in that seminar, you're just thinking about how different it was. That was sort of global scale issues. I was talking about physiological plasticity and in tropical and temperate and wet tropics, dry tropics. So looking at the whole globe. This is a very different talk. I'm talking about a very small question. And I'll illustrate about how small that question is in a minute. But it's something that's been bothering me for about the last 6 years. And so I decided this year we'll try to answer it. So I'll get to exactly what that was in a minute. So I'm going to be talking about, these are people I have to acknowledge. Georgia Kozamalo was a postgraduate student who did a PhD at the University of Sydney, but I was an associate supervisor, and she did a lot of work in my lab, and she did a lot of different measurements on cane toads. That was her thesis. I'll be talking about some of her results. And then more recently, Kimberly Day and Hava and I collected some of the more recent data from last May. So evaporative water loss can be measured, and we measure it for a lot of different animals. It's an important physiological metric. And this just sort of shows you the experimental setup where the air flows in. You dry the air, you measure how much the flow is. There's a sensor, you measure what the baseline is before it gets to the animal, and then you measure it after the animal and then record it on a computer. So that's sort of the setup. And the way we express the data, I'm going to talk about that. And before I talk about the way we express the data is in resistance to water loss. And before I talk about that, I want to talk about conductance, because resistance is a little bit counterintuitive or non-intuitive. Conductance is much more intuitive. It has the units. It's a measure of the rate of flow, rate of movement from, in this case, we're talking about the movement of water inside the toad, liquid water inside the toad to the atmosphere, to the air around the toad. So the units of the conductance are centimeters per second, just like kilometers per hour is the rate you measure your car. But the physiologists use resistance measures, and by definition, the resistance is the inverse of conductance. So you get these very non-intuitive metric units of resistance measures, resistance values in units of seconds per centimeter. So pure water has a resistance of 0. And so I'll be talking about values from close to 0 to higher, going up to positive numbers. So the higher the number, the more resistant, the more likely it is that the more ability that an animal has to hold the water in, as opposed to losing it to the atmosphere. Now, typical frogs, and there is such a thing as, or what physiologists talk about a typical frog, which includes most amphibians, lose water at a rate as if they were a frog of the size, a bolus of water with the size and shape of the frog. In other words, no resistance. They just pour water out into the environment. And that's because the skin of a frog is a very dynamic organ that they use for respiration. It's part of the immune system. It's a very active organ, and it's living cells right on the very surface, whereas a reptile has a dead layer, and most animals have a layer of dead cells on the top. We have dead cells on the top, and it's not nearly as interactive with the environment as the skin of an amphibian. So typical frogs have a resistance very close to 0, but there are atypical frogs, and atypical frogs are really tree frogs, or phylogenetically tree frogs, frogs that are in the tree frog family. And that allows them to climb up into trees where the wind speed, there's wind blowing, and they can go several days without coming back and recharging with water, coming back to the ground or getting water up in the tree somehow. So I'll talk about that different species. So this was work done that we published in 2005. Jean Young was a PhD student, and she measured the water loss rates in a whole lot of local species. All of these are local species. And some of the local species are typical amphibians with a resistance value that's not statistically different from 0. That's all of these. And then there's a second category of those that were statistically different from 0, but still very low. So values from, about 1 to 4. And that's all of these species. And that includes the cane toads, which in that study, we found the resistance value of 1.7 as opposed to 0 for a typical animal. And then there are a group of species that we call moderate species that have moderate resistance values from 5 to say 20. That's the green tree frog, the red tree frog, Ross tree frog. This is the Alice Springs green tree frog. This is the Western Australia green tree frog. And these are a couple of others in the same genus. And some of these are actually terrestrial frogs, but they're phylogenetically tree frogs. So even though they've moved evolved back down into using a terrestrial environment, they still retain that moderate resistance. Other species of Litoria are over here, have completely lost it. Like Microbelos has 0 resistance, Mariana 0 resistance, and some of these have a slight, small, low resistance. And then there's a fourth group. This is the group that have very high resistance. Litoria bicolor is the only local species. There are some other species in Queensland that have really high resistance values. This resistance value of Litoria bicolor, which is shown here, soaking up water off of pandanus leaf, a resistance of about 63. And this is a picture of a cocooned Cyclorhina australis. So Cyclorhina australis in its natural frog form is over here in the low group, but they spend several months of the year in a cocoon. And when they're in cocoon, we measure the resistance values of 219. So, quite high resistance values for a reptile. So here's the cane toads. That's what we'll be concentrating on, 1.7. And so that's represented here on this graph in Northern Territory. In 2005, we measured cane toads with 1.7 seconds per centimeter resistance. And then Georgia came along and did her PhD and measured, among other things, she measured water loss rates from toads from here, from Brazil, Hawaii, Western Australia, and Queensland. And what she found was in the Northern Territory, she got a value slightly higher than ours, but not statistically different from ours. So they would still be in the low category of, with that categorization that I showed in the previous graph. And then the cane toads from Brazil, similarly in the same group. Cane toads from Hawaii, similar. Cane toads from Western Australia. So far, all of these are statistically the same, very low resistance cutaneous water loss. And then she measured some from Queensland and got this statistically different higher resistance. And a couple of things about that point. First of all, I believe it. And I guess the reason for that is she did the work in my lab and used my equipment, and she got a value down here for other groups, other areas that coincide with measurements that I had made. Another point is that unlike these other groups, these frogs were measured straight out of the field. So you grab a toad, the next day you measure its water loss. That's what she took equipment to Brazil and Hawaii and did the same thing. Western Australia were a couple of days delayed getting it back from Kununurra to Darwin. These toads were shipped from Queensland to the lab here at CDU, and they were measured. So that's one difference. So the third point that I want to make about this point is that these Queensland toads came from Charters Towers. Now, that's not a great, if you're going to get a representative Queensland cane toad, you wouldn't pick it from Charters Towers because that's a much drier environment than, say, the sugarcane fields in other parts of Queensland. So the much wetter areas. So this is quite a dry area. So the question is, well, is there something going on here because they're from a dry part of Queensland, or what? And this has been worrying me because, and the reason it worries me, well, let me put this in, I'll put it in perspective, and then I'll come back to the point about why I think that this is worthy of investigation, even though it, and I will first of all just say that we published those reports, we published these results, and in this report, I sort of said, well, we can't say this is evolution because there are other possibilities. There could be, I mean, Rick Shine and his group have shown a lot of evolution of cane toads in Australia compared to other parts, and as they've moved across Northern Australia in different characteristics. And rather than just jumping to that conclusion, there are other possibilities. One of which is it's a physiological response that we really don't understand because there's no real known mechanism for an animal with no resistance to all of a sudden create resistance, or at least not a well understood mechanism. I'll come back to that point. So we sort of covered our bases, but we left it open. What's going on here? We don't really know. And so I decided to accept that. Now, there are data points on this graph, believe it or not. Most of them are right down here. So this is the data that I've showed you before. This is the Queensland. This is the Latoria bicolor, the 60-something. And this is the native house gecko. And most reptiles are up here somewhere. But this is where I gets to the point I have to convince you that this is an important question, that this line is different from all of these other lines. And the reason I think it is important, as you know, a frog physiologist, it's important because the green tree frog is really kind of right there. All of the tree frogs in the Northern Territory, except for bicolor, are all right there. So only very slightly higher. And that a resistance of 10 or 12, 15 opens up a whole new world for frogs. They're able to go up into the trees. They're able to last several days without replenishing in their water, whereas a similarly sized cane toad would suffer from that very badly from going up in a tree. It would lose its water very quickly, and it would have to recharge its water on a much quicker time basis. So ecologically, a small resistance can be important. And the other reason that it's important that to me, that Queensland toads might be different is, well, if it's different, it's the first frog anywhere in the world other than a tree frog that has evolved resistance to water loss. And so that's important. Or if alternatively, if it's physiology, then that opens up a whole nother question. It's really not a well-known mechanism that's working here. to create that distance. So first of all, for those reasons, it's been worrying me for the last 5 or 6 years, and so with Hava's project, the project that Hava's working on skin microbes, we were going to Queensland to catch cane toads anyway for skin microbes, and so I thought, well, all it takes is us packing in another 200 kilograms worth of equipment and setting up a lab, and we'll measure some cane toads at the same time. And so that's what we did. And so the first stop was in the wet part of Queensland, not Charters Towers, but we wanted, this is pretty close to ground zero where cane toads first came to Australia. This is Curramine Beach, which is close in the Innisfail area. And we caught cane toads in this area at night. And then we took them the next day, we took them into the caravan park, set up all this equipment and measured water loss. Did that for a couple of days. And then we moved to Charters Towers, a much drier environment. And as you can see from this slide, it's a completely different environment in Charters Towers, even though the caravan parks all look pretty similar. It was different because this one had room enough for us to sit down in while we took measurements. And so we measured the water loss from the cane toads in these two parts of Queensland. And we also repeated the measurements using the exact same equipment, the same setup back here, catching local toads from on campus. And so that's what I'm going to show you now. So these are the 2005, I've already shown you this. These are Georgia's 2020, or published in 2020 results. And these are all the new results, or the NT 2023. So pretty close to what we've gotten before. So so far, so good. The wet Queensland, this is Curramine Beach. So the beach area I showed you, pretty much the same. So then there's the question. Okay, now this is a dry, this is a Charters Towers toads. Are they going to be like Georgia's, or are they going to be like the other toads? Well, turns out they're like this. So the only ones of all of these that we sampled that really stand out were the 2020, they're measured about 2015, 2016, Charters Towers toads. These are Charters Towers toads, same, caught in the same park actually, and just a few years apart, and they have difference. So what are our conclusions for that? What can we conclude from that? The first conclusion is that cutaneous resistance to water loss has not evolved in cane toads. So it's not, if you take them straight out of the field, measure their water loss, they're not elevated like that. So how do you explain that high value? It's the observed difference is probably related to some physiological effects of transporting toads from Queensland to the Northern Territory. In other words, they were probably stressed in some way, and some stress-related hormonal changes that reduced the peripheral blood flow. And there are ways that this can happen. This is, like I said, it's very not well understood, but there are some publications that show with different pharmacological agents you can make toads keep their blood into the middle of their body, send less blood to the skin, and therefore they lose less water. And there's this mechanism of these things called aquaporins, which are molecular valves, subcellular molecules, essentially, that regulate blood flow from one, say, for example, on the outside of a capillary. They can control the flow of fluids in and out of those capillaries. And we, a few years ago, did a project of water uptake, and we showed that some species of frogs that are aquatic frogs have very different kinds of water uptake than terrestrial frogs. And that's related to the fact that a frog that's spending all of its time in water could very easily become too dilute, could take up too much water, lose all its salts. And so they have these mechanisms, probably using aquaporins to prevent water from coming in. And so what I'm proposing now that maybe the aquaporins can work in the other direction, that is to constrict, keep the blood flow, keep the fluids in the core of the body, not to the periphery, and therefore it doesn't leave through the skin of the frog at nearly the rate. So we've sort of answered the question. We've answered this part of the question. It's not, they haven't evolved. So you can rest easy that cane toads are not evolving into tree frogs. But we haven't, there's still lots to learn about water loss in cane toads. So thanks. Yep.
Thanks, Keith. I was just wondering, is there much known about acclimation of resistance in amphibians in terms of, because I know with fish, if they're, for example, if they're held in like low oxygen environments and then exposed to low oxygen, they're more resistant to that. And does that same sort of thing play out with resistance in amphibians, or is it?
It's never been demonstrated.
Yeah.
Now, what has been demonstrated is sort of like that. There's a few species that have resistance, and then if you warm them up, you get warmer and warmer and warmer, then they start losing that resistance. They change in other words, what happens is the lipids on their skin. So the resistance is a result of lipid layer on the skin, secretions on the skin that are the primary. It's a complex mix of chemicals, but the really active constituent is lipids. And those lipids can change at high temperatures so that the water starts, they lose their waterproofing ability. So essentially, at high temperatures, they start to sweat. In a way, they start losing water to cool down. And so that's, it's not really acclimation, but it's a physiological response to temperature where they change. Other species don't have that ability. And, it's only been shown in a couple of species. The other point sort of related to that is that there's a South American group of frogs in the genus Medusa that have very high resistance rates when they secrete. So in other words, when they're out moving around, they don't have much resistance, have a little bit of resistance. And then during the day, they perch on a limb, just like a tree, like a bird on a tree, and secrete a very thick, waxy substance and actively wipe it over on themselves, and their resistance value goes, right up to a reptilian value. So again, that's not acclimation, but it's a short-term change in their resistance. But that really seems
it's interesting. I was just curious to know, like, if you held cane toads in really dry environments versus really wet ones. But I suppose your comparison of the wet dry season for Queensland probably.
Yeah, no,
it doesn't change with that. Anyway.
Yeah, almost certainly no frog that doesn't have resistance can all of a sudden acquire it. In other words, you've either got it or you don't.
Yeah.
But those that have it, the tree frogs,
can
play around with it a bit.
Yeah.
But nobody's ever actually shown an acclimation response, and we've actually looked for that. We looked at years ago, back in 2000, we tried to acclimate the Toria bicolor and couldn't get any difference. So
thanks.
Yep.
Yeah, thanks, Keith. I wasn't sure with your list whether you had looked at resistance in one of those arid zone burrowing frogs that Australia's famous for.
We really about the only one from the real arid zone is Gilleni, which is in Alice Springs region. But no, we looked at rubella has an enormous range, and we measured them right from Alice Springs to Darwin, all along at every roadhouse we stopped and grabbed them out of the toilets and measured them, and they're the same everywhere. They're not different. But no, I mean, there's a lot of other. There are other Litoria. There are other tree frogs down in the central area that we haven't measured. And there are a lot of, well, more species that do this cocooning thing, which like some of them noted, and which probably don't have much, or probably low until they create a cocoon, and then they'll, you know, get a high resistance.
And a follow-up question, if that's okay, what's Litoria bicolor doing?
What's it?
Why is Litoria bicolor? So it's not cocoon, so it stands out from everything else, doesn't it? And
I think it's related to, well, I'll give you an answer and then I'll give you the reason that answer doesn't work. But the answer is it's so small, and you see them out on really crazy places. You'll see them out in the middle of the day, kind of just perched on a boat or something, you know, and on windows and all sorts of crazy places where if they didn't have resistance, they would, because I mean, they're less than a gram. And so they don't have much water to lose. And so that resistance there keeps it in. And so that's sort of the logical explanation, is they have to have resistance to be a very small tree frog. The reason that doesn't work is because Litoria microbelos looks almost exactly like it, and then they're the same size and they have no resistance, but they're always close to water. So they're living in different, you know, these guys go up into the pandanus, probably spend the whole dry season in pandanus, or in a tree hollow or somewhere. Whereas microbelos, they're close to water. Who knows where they go in the dry season? I've got no idea. I mean, but they're, again, less than a gram. They've got to be close to water, but where that water is, I don't know. I'd really love to know. Well, and all of these are small. I mean, that's probably even smaller than microbelos. So all of those are really small frogs. How they survive the dry season, I've got no idea, or where they go. But it's got to be close to water, because they've got no physiological mechanism to survive the dry season. They've just got to be close to water somewhere.
So the ones that were transported, that switched on something, have you ever been able to simulate that?
No, because we just found out last month or in May that it wasn't evolution. So we haven't really done anything more with that. I mean, I said, the closest that there are literature experiments where they've used drugs to get a similar result, which implies to me that hormones could be involved.
But just a follow-up then is just in terms of the fact that they're an invasive species and they've potentially got the capacity to do that, does that mean it's a bit of a worry?
Oh, no, I'm not sure. Yeah, that's one way to look at it, that it's a capacity, but I look at it really more as what's the word? You know, they're sick. I don't view it as an adaptation as much as they're stressed and they're shutting down, this kind of thing. That's the way I would look at it. Because, you know, we've maybe caught, like, well, I don't know. And we've never measured them straight out of a really dry environment. But even when you find them in really dry environments, they're close to water. You know, you find them down in Wave Hill Station, but they're close to billabongs and things like that. So, yeah. I mean, it's certainly that millions of cane toads die every dry season. do desiccation. And maybe if you caught them right before they died, that you would measure something like that in the real world. But I think it's they're on their way out, sort of thing.
Yeah.
I don't know Ross actually, but I was wondering. Well, thank you first for your presentation, and I was wondering if the age or the sex of the frog play a key role in the water loss.
Yeah, no, we've looked at, we've looked at that, and particularly size. We were interested in the size. So some of these species that have fairly high resistance values, including bicolor and some of these others, we looked at very new metamorphose in adults, and they get it as soon as they start coming out into the terrestrial environment. They've got the ability to secrete the lipids, and so we thought there might be sort of a gradual increase in it, but I think that's a very vulnerable stage. It makes sense evolutionarily that they're very vulnerable when they first come out, and that's probably when they need it, most, or when they need it. It's very important.
And the sex?
Sex, no, doesn't seem to be any difference. It's sort of it's related to the ecological niche, whether they're tree frogs or ground frogs or that sort of thing, but not really.
We're running out of time, but are there any questions online for those remaining for either Chesky or Keith? If the number goes up. You want to see what that chat is?
Pardon?
Will you just see what that chat is?
Oh, right.
Cool. Okay. Well, thanks, guys. And there's a reception outside as usual. This craziness.
Yeah, it is crazy.
Things got unplugged.